Implicit differentiation is a method to find information about the derivative of a function which function is defined by an equation rather than by an explicit expression. For example, the equation x squared plus y squared and that sum squared plus 3 times x squared y minus y cubed equals 0 defines y in several ways as a function of x. For y, the equation is of degree 4. Solving this fourth degree equation gives several solutions, and each solution gives a function. Now one can study these functions by studying the equation itself directly rather than trying to solve the equation. And the method that allows us to do that is implicit differentiation. Implicit differentiation can also be used to derive a method for differentiating complicated expressions. This method is called logarithmic differentiation. We discuss that in the end of this slideshow. Implicit functions are functions defined by equations. A function f whose values y depend on the variable x according to an equation in terms of x and y is said to be implicitly defined by the equation in question. Now an example of this is the equation x squared plus y squared equals 1. It defines the two functions y equals plus square root 1 minus x squared and y equals minus square root 1 minus x squared. The graph of this equation x squared plus y squared equals 1 is a circle of radius 1 with center at the origin. The plus sign in this expression for y corresponds to the upper half of the circle and the minus sign to the lower half of the circle. In this case, it is possible to solve y in terms of x from this equation, and one gets two solutions. If the equations are more complicated, solving y may not be possible at all. The equation x squared plus y squared and that sum squared plus 3x squared y minus y cubed equals 0 defines several functions that can be solved from the equation. Solving is not advisable, however, because it is very difficult. It is best to study these functions by studying the defining equation directly rather than trying to solve y in terms of x. For y, this equation is of degree 4. Now the idea here is that we differentiate equations by the chain rule. And that is best illustrated by examples. So we had the equation x squared plus y squared equals 1. That's an equation for a circle of radius 1 with center at the origin. From this equation, it would be a simple matter to solve y in terms of x. But we may differentiate directly. When we differentiate x squared with respect to x, we get 2 times x. When we differentiate y squared with respect to x, we must use the chain rule. The outer function is variable squared and the inner function is the unknown function y. So when we differentiate y squared with respect to x, we get 2 times y prime, derivative of y. And this now must be 0 because the derivative of 1 is 0. So we get an equation 2 times x plus 2 times y prime equals 0, and from this equation it is easy to solve y prime. One gets y prime equals negative x over y. This gives the slope of the line tangent to the unit circle at the point xy. The slope is negative x divided by y. This information, by the way, can be used to quickly and easily and accurately draw the image of a circle of any radius. In this example, we find the points of the curve x squared plus y squared and that sum squared plus 3 times x squared y minus y cubed equals 0, at which the tangent line is horizontal. We apply implicit differentiation. We do not even try to solve y in terms of x from this equation. Now we start with the equation x squared plus y squared and that sum squared plus 3x squared y minus y cubed equals 0, and we apply implicit differentiation to the left hand side. We must use the chain rule. The term x squared plus y squared squared, when that is differentiated, it first gives 2 times x squared plus y squared, and that multiplied by the derivative of x squared plus y squared. This is by the chain rule. Here the outer function is variable squared, the inner function is x squared plus y squared. But now x squared plus y squared is a function of x, so derivative of x squared is 2 times x, derivative of y squared has still to be computed by the chain rule. It is 2 times y prime. So we get from the first term x squared plus y squared squared the term 2 times x squared plus y squared, and that sum multiplied by 2 times x plus 2 times y prime. Derivative of 3 times x squared y consists of 2 expressions. First we get by the product rule derivative of 3 times x squared, which is 6 times x, times the second term y, plus 3 times x squared times derivative of y, which is y prime. So that gives these two middle terms in this expression, and finally the derivative of negative y cubed is minus 3 times y squared times y prime, and this now must be 0 because derivative of 0 is of course 0. So we have the equation 2 times x squared plus y squared, and that multiplied by 2x plus 2 times y prime plus 6xy plus 3x squared y prime minus 3y squared y prime equals 0. And our task was to find those points x and y at which the tangent is horizontal. And now the tangent is horizontal if y prime is 0. Therefore this equation simplifies to, we simply plug in 0 in place of y prime, and we get 4x times x squared plus y squared plus 6xy equals 0. This can still be written as 2 times x times 2x squared plus y squared plus 3 times y equals 0. We simply take 2 times x as a common factor. So those points xy on the curve at which the tangent is horizontal satisfy 2 times x times 2x squared plus y squared plus 3y equals 0. So we have concluded that points on the curve at which the tangent is horizontal satisfy first the equation 2 times x, and that multiplied by 2 times x squared plus y squared plus 3 times y. This product must be 0. And then the equation of the curve was x squared plus y squared squared plus 3x squared y minus y cubed equals 0. Now one solution to the first equation is that x equals 0. If x equals 0, then 2 times x times anything is 0, in particular 2 times x times 2x squared plus y squared plus 3y is certainly 0. So the first equation is then satisfied. And now if we substitute x equals 0 in place of x in the second equation, we get equation for y, which is y to the fourth minus y cubed equals 0. This has the solutions 0 and 1. Therefore, one solution to this pair of equations is x equals 0 and y equals 0 or y equals 1. So this is a candidate for a point at which the tangent is horizontal. Now if x is not 0, then in order for 2 times x times 2x squared y squared plus 3y to be 0, we must have that the second factor is 0. So then we get that 2 times x squared plus y squared plus 3 times y must be 0 if x is not 0. And from here we may solve x squared plus y squared. We get that if x is not 0, then x squared plus y squared must be negative 3y divided by 2. We may substitute that in place of x squared plus y squared to the second equation. and we get negative 3 times y divided by 2, and that's squared, plus 3 times x squared y minus y cubed equals 0. So we have established a condition that if the tangent at the point xy is horizontal and if x is not 0, then we must have negative 3y divided by 2 squared plus 3x squared y minus y cubed is 0. And we wish to solve for y. Now we remember that if x is not 0, then we had also the condition x squared plus y squared equals negative 3y divided by 2. That was a substitution we used to the original equation defining the curve to get the above equation for y. So we substitute again, in place of x squared appearing in the equation in the middle term, we substitute minus 3y divided by 2 minus y squared, so that we get an equation for y only. And we get in that way minus 3y divided by 2, and that's squared, plus 3 times negative 3y divided by 2 minus y squared, and that difference multiplied by y, minus y cubed equals 0. So we have this equation. And from this equation, every term contains the factor y squared. So we may take y squared as a common factor. If we do that, then of the first term, negative 3y divided by 2, and that squared, remains only 9 divided by 4. That is, negative 3 divided by 2 squared is 9 divided by 4. And from the other terms, we get, after some combination, minus 4y minus 9 divided by 2. And this product must be 0. So now we have two choices. Either y is 0, or 9 divided by 4 minus 4y minus 9 divided by 2 is 0, and this means y equals negative 9 divided by 16. So again, here we have two choices, y equals 0 or y equals negative 9 over 16. We have found that if the tangent is horizontal, then either y equals 0 or y equals negative 9 over 16. If y equals 0, then x equals 0 or x equals 1. This can be solved from the equation defining the curve. And this is also a solution that we already have found. If y equals negative 9 over 16, we must solve x from the equation x squared equals minus 3y divided by 2 minus y squared. And this yields plus or minus 3 times square root of 15 divided by 16. So candidates for the points at which the tangent is horizontal are the points negative 3 square root of 15 divided by 16, and y-coordinate minus 9 divided by 16, the origin 0, 0, the point 0, 1, and the point 3 square root of 15 divided by 16, and minus 9 divided by 16, x and y coordinates. The computation we have carried out shows that if the tangent is horizontal, then the point must be one of these. It does not show that the tangent actually is horizontal at these points. This must be checked by still mechanical computations by substituting these values for the equation that we obtain for y prime by implicit differentiation. This is indeed the case. We have 4 solutions, and they are the 4 points at which the tangent of this curve, the red curve shown here in the picture, is horizontal. Logarithmic differentiation applies to functions which take positive values. The idea is the following. If y is a function f of x which takes only positive values, we may take logarithms from both sides. So if y equals f of x, then ln of y equals ln of f of x. And now differentiating this equation implicitly, from the left-hand side we get y prime divided by y. This is derivative of ln of y with respect to x. We view y as a function of x. And this y prime divided by y is now derivative of logarithm of f of x. This means that y prime is y times derivative of ln of f of x. This logarithmic differentiation rule, y prime equals y times derivative of ln of f of x, applies to functions for which ln of f of x is easier to differentiate than the actual function itself directly. So we use this, for example, to differentiate the function y equals x times sine of x. This is clearly defined only if x is positive. If x is positive, then x to the power sine of x is always defined and a positive number. So we take logarithm from both sides. We get ln of y equals ln of x to the power sine of x. But logarithm of x to the power sine of x is sine of x times log of x. So we have that ln of y equals sine of x times ln of x. And from that, by implicit differentiation, we get the logarithmic differentiation rule, and we conclude that y prime equals y times derivative of sine of x times ln of x. Sine of x times ln of x is easy to differentiate by the product rule. The derivative of sine of x times ln of x is cosine of x times ln of x plus sine of x divided by x. Therefore, we conclude that the derivative of the function y equals x sine of x is y times cos of x ln of x plus sine of x divided by x. So using the logarithmic differentiation rule, y prime equals y times derivative of log of f of x, we obtained that the derivative of y equals x to the power sine of x is simply y times cos of x ln of x plus sine of x divided by x. We still have to substitute y back to the right hand side of this equation. We get the answer y prime, that's the derivative of x to the sine of x, equals x to the sine of x times cos of x ln of x plus sine of x divided by x. This was easily obtained by logarithmic differentiation. To summarize the discussion, I recall that we have considered implicitly defined functions. These are functions which are defined by an equation rather than by an explicit expression. So if the equation is given, then by implicit differentiation one may get lots of information of the function or the graph itself without actually having to solve the function in terms of explicit expressions. An example of such a situation was the curve x squared plus y squared, and that squared plus 3 times x squared y minus y cubed equals 0. Solving y in terms of x from this equation is hopeless, or at least seems to be. But by implicit differentiation, we were able to find information about the tangent lines of this curve. Secondly, we discuss logarithmic differentiation. The logarithmic differentiation applies to functions taking positive values only, and for such functions, the derivative y prime equals a function value times the derivative of log of the function itself. And this can be applied to functions for which log of the function itself is easier to differentiate than the expression for the function. An example of such a situation is y equals x to the power x, where x is positive. Now then, y prime by logarithmic differentiation is y times derivative of logarithm of x to the power x, but logarithm of x to the power x is x times logarithm of x. So y prime is y times derivative of x times ln of x, and it is easy to compute derivative of x times ln of x using simply the product rule. The derivative is x times derivative of ln of x, which is 1 over x, so x times 1 over x, which is 1, plus ln of x times the derivative of x, but derivative of x is 1, so we conclude that derivative of x times ln of x is just 1 plus ln of x. So we conclude that the derivative of the function y equals x to the power x is y times 1 plus ln of x, and we substitute back in place of y what it was in terms of x, and we get that the derivative of x to the power x is x to the power x times 1 plus ln of x. In this way, logarithmic differentiation was a nice trick to compute the derivative of a rather complicated function.